Hello, everyone, and thank you for attending this presentation. My name is Pat Bhattacharya, and I'd like to welcome you to today's webinar on AI-driven asset-aware risk and collections. Joining me today are my colleagues Krishna Mehta, Jisha Augustine, and Shikha Agarwal. Today, we will discuss how artificial intelligence tools, particularly computer vision models, can help us more effectively manage credit risk and collection strategies. More specifically, we will explore credit risk and default behavior after funding. While industry attention is heavily focused on developing credit risk models for funding decisions, funding is not the finish line. Equipment finance companies can suffer significant losses post disbursement. Although the ideal scenario involves seamless asset delivery, insurance, and possession, numerous issues can arise, causing some of the biggest financial losses to occur after the money has been released. Let me take a moment here to give some examples of some of the issues that can arise post funding. One example is fraud where the asset never arrives. Another possibility is that the asset arrives, but once in the field, the financed equipment is swapped for older or cheaper units, or maybe the financed equipment is quietly relocated or sold off, or stripped for valuable parts which are sold off. The asset may also be abused. For instance, it may be overused or underused in suspicious ways. These are just some examples of the issues that can arise post-funding. When assets are not used for their intended purpose, delinquencies often follow, forcing equipment finance companies into a cycle of collections and repossession. Once the equipment is repossessed, the lessor must determine the best method to recover its remaining value. At this stage, lessors typically obtain a valuation to understand the potential asset value, dispatching agents to photograph the asset, and hiring experts to assess its condition. Since the cost of hiring agents and experts are high, lessors evaluate the condition of assets less frequently. Most of the time, the condition of equipment is only evaluated after delinquencies and failed collections. However, by that time, the lessor's asset may already be either missing or in poor condition. Therefore, we ask the question, is it possible to more easily assess the condition of the asset? If we can do so, that may enable us to do more frequent checks on the condition of the equipment, and that in turn will allow lessors to recover more of their losses in this situation. Recent developments in AI-based computer vision models allow us to automatically identify the condition of assets from pictures. These neural network models are inspired by the structure and function of the human brain and are very good at image classification. In fact, in recent years, image classification has seen major advancements, with deep learning models sometimes achieving above human level performance in object detection and recognition. Computer vision can effectively identify if an item is in good or bad condition, and these models often surpass human accuracy and speed in industrial settings. By analyzing images or videos, AI algorithms can detect flaws like cracks, dents, scratches, discoloration, structural defects, etc. And this even allows for real-time quality control. As we will demonstrate later in this presentation, our trained models accurately predict asset conditions in holdout samples with results that generalize across various types of equipment. We trained our models using images for excavators, but the same model was also able to predict the condition of other equipments such as tractors, bulldozers, and forklifts. Another key point I would like to emphasize is that we train these models using synthetic images. We did this for two reasons. First, synthetic data was more readily available. Secondly, we realized that if a model built on synthetic data performs well on real data, the results are far more powerful as they can be applied to scenarios where real imagery is proprietary or simply not available. My colleague Jisha will walk you through our modeling methods and results later in this presentation. As we worked with these synthetic images, we asked ourselves, can fraudsters generate fake images of pristine equipment or manipulate existing asset photos? How can we detect if an image has been synthetically generated or altered? We explored techniques to identify these forgeries, and my colleague Shikha will discuss some of these methods later in this presentation. And now, without further ado, let me hand over the presentation to my colleague Jisha, who will take you through our model building methodology and results.
Thanks, Pat. Hello, everyone. My name is Dr. Jisha Augustine, and I will take you through some of the methodology and result. We used stable diffusion to generate synthetic excavator images. Stable diffusion is a latent diffusion model that can generate photorealistic images from any text input. Normally, diffusion models start with random noise and gradually remove that noise step by step to create an image. But instead of working directly on images, stable diffusion works in a compressed latent space. This reduces both memory usage and computation, making the model much faster and efficient compared to traditional diffusion models. Stable diffusion mainly has three components: a variational autoencoder, which compresses images into lower dimensional latent space and later reconstruct them back. Unit, which is the core model responsible for removing noise step by step. Text encoder, usually a pre-trained frozen language model, which converts the input text into embeddings so the model can understand and follow the prompt. Now, let us look at how the model generates an image step by step. We input a text prompt. The text prompt gets projected into a latent vector space by the text encoder. Then a random noise image is generated and this text information is concatenated with it. The unit then gradually removes noise over multiple steps while being guided by the text. With each step, the image becomes clearer. Finally, the cleaned latent representation is passed through the decoder, which converts it into a clear and realistic image. Now, let me talk about the dataset we worked with. We used synthetic excavator images in both good and bad conditions for training the model. As mentioned earlier, these images were generated using the stable diffusion model. In addition to the synthetic images, we also tested our model on real excavator images to evaluate its performance on real world data. The model used for the classification of these images into good and bad is ResNet 18, which is a residual network with 18 layers. A residual network is basically a convolutional neural network with skip connections which allow gradients to flow more easily and help to overcome the vanishing gradient problem during training. ResNet 18 is efficient and lightweight and is widely used as a baseline deep learning model for image classification tasks. Next, we will talk about the results we obtained from our experiment. This slide shows the results of the model when it was trained, validated, and tested using only synthetic excavator images. The training AUC is 1.0, the validation AUC is 0.99, and the test AUC is 0.97. The model performed very well on synthetic data. This is because synthetic images provide enough variety to help the model learn the conditional differences effectively. In addition to synthetic images, we tested the model using real excavator images to see if it could generalize beyond synthetic data. On this real world dataset, the model achieves an AUC of 0.96. This demonstrates that synthetic data can effectively train models that generalizes well to real world scenarios. Then we asked, can the model generalizes to equipment it hasn't seen? We tested bulldozers, forklifts, and tractors to find out. The AUC of bulldozers is 0.86, forklifts is 0.98, and tractors is 0.89. Even on unseen equipment types, the model performed well. Rather than simply memorizing specific images, the model is effectively learning the underlying patterns that indicate equipment condition. Now, I would like to share an interesting finding from our experiment. We had two identical images, one zoomed in with less background and the other zoomed out. When we scored them using our model, we noticed something strange. The zoomed in image was classified correctly, while the zoomed out one was not. We then cropped and zoomed in the misclassified image and rescored it. And this time, the model predicted it correctly. To test if this worked for other misclassified images, we selected more images, cropped the background, and zoomed in. Some were classified correctly, but others still weren't. From this, we can conclude that cropping and zooming won't fix all misclassifications, but providing zoomed in images with less background may improve the model's prediction performance. We successfully built a good model by training it with synthetic images. The next question is, could vendors also create synthetic images and use them as fraudulent pictures of equipment? I will now hand over to Shikha, who will talk more about this. Thank you.
Thank you, Jisha. Hello, everyone. My name is Dr. Shikha Agrawal. As Jisha mentioned, images of assets can be easily manipulated or AI generated, allowing fraudster to hide equipment damage from lessors. This makes image authenticity verification a critical challenge. I will present methods for detecting digital tampering by analyzing intrinsic image evidences. The core approach involves analyzing hidden patterns with an image to detect alterations. Image verification is based on a simple assumption. Authentic images exhibit internal consistency where all regions follow uniform patterns. However, manipulated images introduce inconsistencies because edited areas stem from different sources or processing histories. This slide explains how image forgery can be detected. Hidden internal properties within the image are first extracted. These internal hidden features include metadata, compression behavior, noise, and frequency structures. Then these features are analyzed to find inconsistencies which indicate possible image manipulation. This slide explains some of the different techniques used for image forgery detection. There are many methods and a few commonly used ones are explained here. Each method analyzes a different property of the image. EXIF analysis examines metadata such as camera details, timestamps, and software information stored as hidden information with image. This EXIF metadata can be used to identify image sources and potential editing traces. Error label analysis or ELA detects variation in image compression. Modified section has different compression values, therefore, modified area appears brighter in ELA image. Noise analysis checks whether the camera noise pattern is consistent across the image. A modified section of the image will have different noise pattern. And frequency domain analysis using fast Fourier transformation converts the image into frequency representation which can identify irregularities in structural pattern of the image. This slide explains the complete workflow of the forgery detection system. The process begins with an input image. EXIF analysis begins by extracting metadata from the image. The metadata is then checked for the presence, consistency, and software information. Any missing or inconsistency in the metadata may indicate possible editing. Next, error label analysis starts by recompressing the image. The recompressed image is compared with the input image to measure compression differences. Part of the image with higher differences are highlighted as potential edited areas. Frequency domain analysis using fast Fourier transformation converts the image from spatial domain to frequency domain. The frequency distribution is then analyzed to check for consistency. Any abnormal spikes or repeated patterns may indicate manipulation. Noise pattern analysis extracts the camera noise from the image. The noise is analyzed across different regions to check consistency. If the noise pattern varies significantly, it may suggest that some section of the image were taken from other source or has been altered. Finally, for strong evidence, result from all the methods could be combined. If multiple inconsistencies are observed across these analyses, the image is confidently classified as potentially tampered. Each method acts like a different lens, and combining them gives a more reliable decision. Next, I would like to show you some examples of how these techniques work with a manipulated image. First, let us look at the original image shown here on the top left side of the slide. For the purpose of this experiment, I have manipulated this image by adding some pink flowers as shown on the image on the right. Now let us look at the ELA representation of both these images. We can see that ELA clearly highlights the edited region as the edited region shows higher compression differences. On this slide, we show the result of noise analysis on both images. From noise pattern of the images, we can see that noise analysis also reveals inconsistencies where the edited region exhibit a denser noise pattern compared to rest of the image. On this slide, we show the result of fast Fourier transformation analysis on both images. We can see that in this case, the FFT result does not show any strong indication of tampering. This is because FFT methods are better at detecting global manipulation rather than local tampering of the image. So, even though this method did not work on this particular scenario, there are other cases when FFT works well. The key conclusion of our discussion is that image manipulation introduces internal inconsistencies that can be detected through image forensic analysis. Each methods provide a different perspective. Like ELA methods highlights compression differences, noise analysis detects sensor inconsistencies, and fast Fourier transformation analyzes structural patterns. EXIF metadata tells us about camera details, creation time, modification time, which are useful signal for identifying potential image editing. However, relying on a single method to detect inconsistency may not be sufficient for accurate detection. For instance, ELA and noise methods can capture local edits better, but fast Fourier methods is not good at local editing detection. By combining multiple techniques such as ELA, noise, and FFT, a more reliable and confident decision can be made. Thank you, everyone. I will now hand over to Krishna to summarize the overall discussion.
Let me now share some insights from these experiments with you. The first thing is that the ability to proactively monitor the assets transforms collections. So, in asset based lending, instead of being reactive and responding to delinquencies, uh, lenders now have the ability to use AI driven asset monitoring, and using this, they can now reduce the delinquency risks as well as tackle many cases of fraud. And this will lead to direct improvement of the profitability of the organization. Now, the next thing is that this becomes very lightweight with the introduction of artificial intelligence, because you don't need to constantly send people mm, to check on the equipments you have financed anymore. Just ask for a picture and AI will do the rest. And that is very powerful. And then uh, a worry would be that there are so many different types of equipment classes. And do we need to build models for every one of them? That can be very overwhelming. But we don't need to, as our experiments have shown, that you can have a general model for a class of similar equipments, and the model does very well. And because of that, uh, the deployment overhead is significantly reduced. The cost of training these models is significantly reduced, and it becomes a lot easier to adopt this approach. And then, all these points apart, often the biggest bottleneck is data. Where do we get enough data to train our models? Who has this kind of data? What if we are going into a new area, or we have not collected these images in the past? All these were fair concerns, but using synthetic image, it takes away this problem. In fact, we are seeing in our experiments that synthetic images cover uh, a lot of different types of cases and actually lead to superior models. And because of that, uh, uh, the burden of data collection is significantly reduced. You still need real data. You need to validate these models, you need to tether them to reality. And so you need the real data. But the burden and the volume of data needed is significantly reduced. And because of all these points, it becomes a really viable option to now use AI driven asset monitoring and reduce the risks faced by the organization. We hope you found this session to be useful. We want to thank you so much for attending this webinar, and we look forward to having you again for our next event. Thank you so much.